Okay, so we were discussing that depending on the application, we can select the appropriate material. Okay, so for example, if you want to design your envelope, you will try to select materials with relatively low conductivity. In other applications, you need to have good transfer. Okay, and because you need to transfer your energy from one form to another form. So let's say you have an application where you need to have high conduction to transfer maximum of energy, then you should select materials characterized by high conductivity. Now, in this table, we have ranges, if you want, some typical values of conductivity, and we can see if we compare values that for metals we have relatively large values compared to glass, windows, and rubber, and on the other hand, also for water and air we have relatively small thermal conductivity. And as we discussed previously, air is one of the best insulators because it's characterized by a relatively very small value of K. And this is why we add it as a layer when we put envelopes. Okay. Let us do a small example on conduction. So the wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick, having a thermal conductivity of 1.7 watt per meter Kelvin. Measurements made during steady state operation reveal that temperatures of 1,400 and 1,150 Kelvin at the inner and outer surfaces respectively. What is the rate of heat loss through this wall that is 0.5 times 1.2 meter on a side? So this is a straightforward example to show you how we can calculate rate of heat loss by conduction in case of steady state. So here all you have to do is to do a small scheme to put what you know about this problem. So you have from one side you have a temperature of 1,400 degrees. From the other side, you have a smaller temperature of 1,150, sorry, in Kelvin, not degrees. Okay. And because they told you it's a steady state operation and you don't have any generation of heat within your wall, you can directly say then the variation of heat inside your wall is linear. And of course, your heat flux will go from the largest temperature side to the smallest temperature side. And just to calculate this rate, because I asked for the rate in watt, so it's a Q, all you have to do is Q is equal to, you can directly apply the formula here. It's K times A times delta T in absolute value, largest temperature minus smaller temperature, over the thickness of the wall. You have all information needed. Just please pay attention for units. So here already all units are well given. In case, for example, you have thickness in millimeter, don't forget to convert it to meter. So you have K is 1.7. Your area is 0.5 times 1.2. Delta T is the difference 1,400 minus 1,150 over the thickness, which is 0.50. Now, for example, they can ask you what can be done to reduce the heat transfer, okay, from the wall of this industrial furnace. What you can do, you have several possible strategies. Or you increase the thickness, okay, or you add a certain, for example, layer of different material characterized by a relatively high, a relatively low conductivity, okay, etc. Yani, you can have several strategies to reduce a heat flux through a certain layer. Now we move to the introduction of convection. Okay, so as we mentioned, we have convection can take place in several forms, but in general, one definition that is common to all forms is that convection is the heat transfer between a moving fluid and a surface which are at different temperatures. And the convection transfer can be comprised of two different mechanisms. The first one is energy transfer due to random molecular motion. And this was the example, if you want, due to when we have density difference, because density difference will lead to random motion of molecules, since molecules will move up while others will replace them. And the second mode that majority of you are familiar with is energy transferred by the bulk motion or macroscopic motion of the fluid. So let us discuss these two types. The first type was already discussed, if you want, when we consider the example of fire. So we can repeat it in brief here. The idea is whenever you have contact between a hot surface and a fluid, molecules at the lower level will be heated. And because we know in general that a higher temperature lead to lower density, the hot molecules will tend to move up, and then cold particles at the largest, cold molecules at top level will replace them. And this will create like motion of the fluid particles within the system. And this random motion will enhance heat transfer. So this is the first type. It's convection because it's involving motion. But here it's random motion of molecules. On the other hand, another type of convection is the one caused by bulk motion of a fluid. What do we mean by this bulk motion? Let's say you have a surface that is at high temperature and you want to cool it. One good strategy to cool it is to pass over this surface a fluid at high velocity. So I can, let's say, flow over this surface. This moving fluid, we call it bulk motion because it will move at a certain velocity over the surface. Due to this bulk motion over the surface, what will happen is that the moving fluid will transport heat as it's moving, okay? And this will lead to cooling of the surface by convection mode, because the moving fluid will transport heat. And then we say that we have heat transfer from the solid towards the fluid by convection. Even here, conduction is involved. You know how? You know that particles of air just in contact with the surface will have zero velocity because of the non-slip condition. We know in fluids that if you have molecules at direct contact with a surface, they will have they should be at same velocity of the surface. Since here the velocity of the surface is zero, then just the molecules that are adjacent to the surface will be characterized by zero velocity. And therefore, the heat that will leave the solid, it will leave it in conduction form, because you know that within a solid, mainly heat is transferred by conduction. And this heat will be transferred to the particles just adjacent to the surface, which have zero velocity, by conductive flux. And now this conductive flux will be transferred to the remaining fluid apart from the surface by convection, because what will happen is that the conductive flux will be convected by the fluid. And in steady state case, we can write that the Q conduction at the surface level, so Q conduction at, let's say this is the surface level and I take y-axis upward, okay? Q conduction at y equals 0 will be equal to the convected flux in case, of course, in case the only mode of heat loss is by convection. Sometimes we'll see in the course also, you can have heat loss by both convection and radiation. Then you should sum the two fluxes. But here we are just considering heat loss by convection. So you say that Q conducted through the air molecules at y equals 0 is Q convected by air. And this will be the equation governing cooling of your surface. Okay. Any question on this?
Professor, just one question. Diffusion, it's basically convection due to diffusion is basically like due to buoyancy, right? Like it's convection due to buoyancy
No, look,
specifically.
what will happen
not-
here, to imagine more what will happen, okay? If you consider a very small cell close to the surface, okay? For this cell, what will happen, you will have a heat flux coming through the cell due to conduction process, okay? Because it's coming from, if you want, from the surface, and just at contact with the surface, you have like still air, okay? So you can say, if you want, that Q conduction in the metal of your in your solid is equal to Q conduction of air at y equals 0, because what will happen, the conductive flux that is lost from the surface is received by the air molecules that are still, okay? And then it will enter this small control volume. This conduction flux that is coming from the solid through air at y equals 0 will be convected because of the fluid motion. Yani imagine that your fluid is moving, then you will have a flux entering at a certain energy entering this phase, and here you will have a flux exiting the phase. But because you are receiving a flux, what will happen to the energy of the convected flux at the outlet? So if you compare the convective flux at inlet and convected flux at outlet, which one will be larger?
The outlet.
At the outlet, because you are transporting heat of conduction, okay? So we say then that we are cooling the surface by convection mechanism, because the heat will be convected within the fluid, and this will lead to increase of the energy of the fluid.
Indeed.
Okay.
Indeed.
So it's not here, in this case, it's not because density difference, it's because you are transporting heat, and this will lead to increase of the temperature of the fluid that is going through the surface. Okay.
Thank you, Professor.
Welcome. Now, as you can see, the process of convection is really little bit much complex than conduction, and it's affected by several parameters. To understand better how we write the convective flux, let us look to explore together convection will be affected by what. First, you know that larger is, of course, the surface area of contact between your surface and your fluid, okay? Larger will be the heat transfer by convection. So that's why we expect to have the area term within the heated transfer. Now, of course, also the heated transfer by convection is mainly due to the difference in temperature between the surface and, if you want, the surrounding temperature of your fluid. You know that your fluid is blown at a certain temperature that we call T infinity, okay? So this is the temperature, the initial temperature, if you want, of your flow as you blow it over your surface. We know that when you have the flow over the surface, this will create some gradient of temperature within the flow. Okay, why? Because the air molecules or the fluid molecules just in contact with the surface will have the highest temperature, which is T of the surface. Okay. However, as you move far from your surface, you have decrease in temperature until reaching T infinity, which is the bulk temperature of your fluid. Okay. Of course, here we have complex phenomena taking place, and will not go over them in this course. That's why, if you want to avoid treating complex issues, in order to get the convective flux, we use empirical relations. What do we mean by empirical relations? We do some experiments, okay, in convection that will help us to define a convective heat transfer coefficient that will be affected, let's say, by the velocity of the flow, because you know that you have several parameters that will affect your convection process. Larger the velocity of your flow, larger will be the convected heat flux, plus the fluid, the type of fluid will also affect convection. You know that if you blow water on a surface, it's not like if you blow air. If you take the example of your car, the thermal combustion that is taking place in your car will lead to very high temperature of your engine. Your engine need to be cooled. You don't rely only on cooling by air. You should cool by water, or you should cool by a refrigerant that will be characterized by a relatively high convective coefficient. So this convective coefficient is really affected by different parameters. And that's why we need to perform experiment to determine it. And then once we do these experiments, we can use like summarize results in tables and in charts. Therefore, you can assess in a simple way the convective flux by saying that it's equal to a certain convective coefficient that is affected by the velocity of the fluid, the type of the fluid that is used to cool or to heat the surface, in addition to the main parameters that we already discussed, which are the area and delta T. Okay, so we can say that convection is mainly affected first by the temperature gradient between the two medium in contact. And we considered the case here of one body that is moving with a certain velocity. This is why we called it bulk motion of the flow, and another that surface that is in general fixed. And the other parameters that will affect convection will be the fluid velocity, in addition to thermal physical properties. Thermal physical properties will be affected by the type of fluid. So cooling with air is not like cooling by water. Water is much more efficient to cool than air. Okay, so this will be related to the type of the material we are using. So now, as a summary, the rate of heat transfer, Q second, can be given here. Also, we can talk about a flux and a rate. The flux is per unit area, so its unit is in watt per meter square. The convective heat transfer coefficient unit is in watt per meter square Kelvin. In case you forgot the units, you can easily get them again. Why? Because you know that heat flux is in watt per meter square and delta T is in Kelvin. So to have homogeneous units, H should be in watt per meter square Kelvin, since when you multiply by delta T, Kelvin and Kelvin will cancel out and the unit will be watt per meter square. And in case you want to calculate the heat rate by convection, then you should do H times A times delta T, where delta T is the difference between the surface temperature and the, if you want, the fluid temperature far from the surface. Now, as we mentioned, the convective heat transfer coefficient is really a complex coefficient because it's affected by several parameters, as the nature of the fluid flow, the fluid velocity, the fluid properties, and the surface geometry. That's why we often determine it by experiments rather by theory. And then we can use some tabulated forms or some graph forms in order to find the value of H. So here, for example, we have typical values of convective coefficients. So we can talk about gases and liquids. You can see the difference. Convective coefficient for gases is much lower than with liquids. That's why when you want to cool and you have very high temperatures, it's much more efficient to use a liquid than a fluid. Now, another, if you want, aspect to consider for convection, you should differentiate between free convection and forced convection. Okay. In general, free convection rely on difference in density. Okay, so it's mainly driven by density differences, and it involves relatively small velocities. So this is the case of, let's say, the example that we talked about before. So whenever, let's say, you have you heat from a certain level, you heat molecules of a fluid at certain level, the density will be reduced, and this will lead to upper motion of the fluid. So here we can talk about convection due to density difference, and the velocity involved for fluid motion will be relatively small. So this is why we talk about free convection in this case. For forced convection, you have external source that is blowing fluid. So you can have a fan, you can have a pump that is forcing your fluid to have a certain velocity, and this will lead to a more effective heat transfer, because this will lead to larger values of H. Okay, so you can compare first gases and liquids, and then you can see the difference between free and forced convection. In forced convection, you have much larger values of H. Convection can also, if you want, be characterized in case you have phase change, or in case you have boiling and condensation. And in case you have boiling and condensation, you can have very large values of heat transfer by convection, because boiling and condensation processes will involve really high rate of heat transfer, and this is linked to high values of convective coefficients. So now, let us consider the following example to understand how we can have energy transfer by different modes. So if you consider the cooling of a hot block by blowing cool air over it, first you have conduction mode of heat transfer, because energy will be first transferred within your solid. It will be transferred by conduction, plus it will be transferred to the air layer adjacent to the surface of the block, also by conduction. Now, this energy is carried out away from the surface by convection. That is, by the combined effect of conduction within the air and the motion of air, you can remove heat near a surface. So this is a process involving both conduction and convection heat transfer modes. Now, to summarize, the equation in convection in case of, if you want, 1D, okay, can be given by Q second equal to H delta T. Here we are finding the flux per unit area, and this is called the Newton's cooling law. And we can see here in this figure the development, if you want, of variation of velocity and variation of temperature. As we discussed together, whenever you have forced convection, you are blowing airflow over a surface. You know that when the flow will be in contact with the surface, near the surface, you impose a zero velocity because of the non-slip condition. And this will lead to variation of velocity from zero until reaching U infinity. U infinity is the velocity at which you are blowing your fluid, okay? And this will create what we call development of a boundary layer. But as we discussed together, what is happening here is really complex, and we will not tackle it in this course. So just you need to know that you will have creation of a zone of variable velocity and a zone of varying temperature, and you can reach T infinity, which is the temperature of your bulk flow far away from the surface. And you can lump what is happening here by one equation, stating that the heat that is convected out from the surface will be calculated by H, which is a convected coefficient determined experimentally, times delta T. And in case you want to find the rate, just you have to multiply by the area. So in summary, convection is called forced convection if the fluid is forced to flow in a tube or over a surface by external means such as a fan, a pump, a mixer, or wind. In contrast, convection is called free or natural when the fluid motion is caused by buoyancy forces induced by density differences due to variation of temperature in the fluid. And a final type is boiling and condensation, which will involve phase change, and is also considered as a convective process because it will lead to fluid motion. In the following figure, we can explore the different types of convection. So here, for example, if you have an electric circuit components that are heated and you want to cool them, okay, if you force air to move over them by a fan, this is forced convection. While if you just rely on air in your room, okay, to cool your system, then you are considering natural convection, and then air that is in contact with your heated element will be will have lower density, and then this will create like air motion by due to difference in density, and this will cause natural convection. So this is an example of forced convection. This is an example of natural convection. Concerning if you want also an example of motion by density difference, you can take also the example that we discussed before. But once you reach, if you want the temperature of evaporation, then what will happen is that you will have formation of bubbles, and the formation of bubbles will lead to motion of your fluid molecules. So you know this, whenever you heat water, you start to see vapor bubbles. This will lead to circulation of liquid molecules within the system and mixing within your container. And the final mode of convection is also by, which involve phase change, is by condensation. So whenever, let's say, you have most air moving through over a surface, and what will happen is that you will have condensation of water droplets on your surface. Now, the third mode of heat that we'll discuss together is radiation, okay? And we already know that any matter that is at non-zero absolute temperature can emit thermal radiation in the form of electromagnetic waves because of vibrational and rotational motion of the molecules. So radiation does not require a medium to take place. This is one of the main difference between radiation and conduction and convection, because to have conduction and convection, you need a fluid, or you need a solid to have transfer of heat by conduction and radiation. However, in the case of radiation, even if you have an empty space, but you have surfaces at different temperature, you will have heat transfers between them by radiation. And radiation will be affected by the level of temperature of the surface. Larger the temperature of the surface, larger the radiations that can be emitted from the surface. That's why the sun is one of the main sources of radiation. And when we'll discuss together after, let's say, global warming, will of course involve radiation flux from the sun, okay? Now, how to quantify radiation? We'll see that radiation will be affected by the waves, the electromagnetic waves ranges, okay? We'll not go into, if you want, the details about how to deal with the different waves, but just for you to know, you know that waves can vary in a large extent, and you can classify them from gamma rays to X-rays to ultraviolet, infrared, microwaves, etc. Now, in this course, we'll be mainly interested with the visible range, okay? So we can work with the visible range, and we can work also with the, we'll be interested into this range also here, the ultraviolet and infrared, because we'll see that this will affect also when we study the greenhouse gases emissions. This range will affect our processes. So we'll be interested to know, to study the range from ultraviolet to infrared, okay? And we'll discuss this in more detail when we talk about the global warming effect. Now, we need to quantify radiation, okay? So we need to just introduce the equations that can give us radiation flux. First, we need to know that we differentiate between several materials. We can talk about a black body material. Whenever we say we have a black body, this means that it's a perfect radiator. So a black body is a body that can emit the maximum possible power at a specific temperature. In real life, the majority of surfaces are not black bodies. They are characterized by a certain property called emissivity. So in this course, we'll give you the value of the emissivity of the surface. This will allow you to quantify the amount of radiation emitted from the surface. So a perfect radiator is a black body that can emit the maximum power at specific T. If I consider any other body, and we'll discuss, for example, gray bodies will have a lower emitted flux, and we can say that Q emitted, if you want, by a gray body, and we'll discuss in a while what is a gray body, over a Q emitted by a black body is equal to epsilon. Okay, and epsilon is a characteristic of a surface called emissivity. Okay, now a black body emission is calculated through the following formula. How we got the formula, just for your knowledge, as we mentioned, we have electromagnetic waves that can cover a larger spectrum. Okay, so if you consider all possible range of wavelengths and you integrate, so you sum all possible emissions, you come up with a total emitted flux of sigma times A times the temperature of the surface to the power 4. First, A is the area. So as expected, larger the area, of course, larger will be the emission. Larger the temperature of the surface, larger will be the radiated flux. Now, the Boltzmann constant is a constant that we obtained when we did the integral procedure, and the value of it will be given for you, of course. So just you should know that it's a constant, and you always use it when you want to calculate a radiation flux. Now, in case your surface is not a black body, you need to add to this. So this is for black bodies. This is Q emitted by a black body. In case you have a gray body, should multiply by epsilon, where epsilon is the emissivity of your gray body. Okay. Now we'll see what do we mean by gray body and how we define it. So all solids, liquids, and gases can emit, absorb, or transmit radiation at variable degrees. Radiation can be considered as a surface phenomena for solids that are opaque to thermal radiation, like, let's say, metals, wood, rocks, since the radiation emitted by the interior regions of such material can never reach the surface, and the radiation incident of such bodies is usually absorbed within a few microns from the surface. What do we mean by this? In general, radiation is a surface phenomena, okay? Especially for the majority of surfaces that we know. Why? Because solids are opaque, okay? What we mean by this, whenever they receive a certain radiation flux from hot surfaces, for example, okay, this received flux will be decomposed mainly into two parts. One that will be reflected, so that will not enter the material. Another one that will be absorbed, okay? But the absorbed part will be trapped with a thin layer of the surface. It will not be transmitted to the remaining part of the solid. And therefore, this absorbed part or can be stored, or can be, part of it can be emitted back by the surface, okay? So we say then that we can define, in case of opaque surfaces, all processes are just taking place at surface level. This is why we say that radiation are considered as surface phenomena, because the whole process is taking place at the level of the surface. And a gray body is defined such that the monochromatic emissivity epsilon is independent of the wavelengths. What do we mean by this? We discussed that we have a range of wavelengths. A gray body is a body that will have the same emissivity epsilon, whatever is the wavelengths, okay? So its emissivity will not depend on the wavelengths. This is why we call it monochromatic emissivity. So this means that it will be the same for any value of lambda. So this is called a gray body. So mainly the gray body can have an emissivity between 0 and 1. And this monochromatic emissivity is defined as the ratio of the monochromatic emissive power of the body to the monochromatic emissive power of a black body at the same wavelengths and temperature. What do we mean by this? We mean that epsilon is defined as the ratio of radiation emitted by the gray body over the radiation emitted by the black body. We know that the black body will emit the maximum, and the gray body, depending on its emissivity, if it has a high emissivity, then it will have a close behavior to the black body. However, if it will emit a small amount, so when epsilon tends to 0, then the behavior of the gray body will be far from the black body and will have can have until 0 emission. Okay. Now, all solid opaque bodies around us are considered gray body. This is why whenever you want to find the emitted radiation flux, the formula that you will use is epsilon, which is the emissivity of the body that will be given to you, times the area, times, if you are considering the rate of radiation, times sigma, which is a constant, times the temperature of the surface to the power 4. So this is how you can calculate the emitted flux. So as we discussed, okay, the flux is sigma t to the power 4. The rate for a black body. For a black body, the rate is sigma times area times t to the power 4. While for a gray body, we should add epsilon. So here, in case we are calculating in watt per meter square, we just do epsilon sigma t surface to the power 4. In case we want to find the rate in watt, we should multiply by the area of the surface. Now, a simple radiation problem that will face a lot in our problems is heat transfer between a surface at temperature T1 that is completely enclosed by a much larger surface maintained at temperature T2. For example, if you take a box and you put it in a furnace, okay? In this case, what will happen, you have a very large surface that will emit radiation, and radiation will be trapped by the surface of your box, and then you can calculate what we call a net rate of radiation that will learn how to find together. Okay. So look, I will open a new session to continue this idea.